I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray that you be with us today. Help us to glorify you, what we do, Lord. In your name I pray. Amen. Okay, so I finally got some common sense and wrote up the proof on a piece of paper so that I don't have to write it out in front of you here. Ay, so much writing. So, but we should talk about it. Start by talking about the stuff we talked about last time. So this is Maschke's theorem, which, I mean, what it says isn't particularly surprising, I suppose, but basically once you have this divide, and it's kind of a divide and conquer thing, right? Like once you have this, you can just kind of start taking a module and just hitting it over the head with this thing over and over again and chipping it down and down and down until you have sort of these undividable blocks, you know? So irreducible, I think, is what those are called. But so again, you know, if we can construct this, and this is an important point here, you guys, I didn't emphasize this last time, but if we have, so we're looking U is an FG module, and you know, V is an FG module, U is a submodule rather. So that means a bunch of things. In particular, it means that U is a submodule. It also implies that the action of the group on that subspace U is invariant. In other words, that G dot U is again in U for any G and any U. But one of the things that I didn't emphasize enough last time is that if you have number 1 is true, number 2 automatically follows. Yeah, pi of V is in U, so exactly. So, right, so 2 automatically follows from 1. So if we can prove 1 for our construction, it automatically gives us 2. So basically we need, and the other thing of course we need is that it's an FG module homomorphism, which means here that we can basically pull the group action out of the map. So like pi of G dot U is G times pi of U. We also need that identity. So again, as we discussed last time, but I'll review briefly. If we had such a homomorphism, a FG module homomorphism, if we said W is the kernel of the homomorphism, then W is a submodule because of the first because of, I don't even know where that's from. I mean, that's the theorem we've had for a while. We had it for vector spaces. Then we also got it in group theory. Then we got it in ring theory. And then it's again true for modules, right? That the kernel of a map. I mean, this is sort of a generic thing. The kernel of a map in some mathematical setting, it's going to be a subobject of whatever you're looking at, right? This is sort of those sort of categorical things. Anyway, if Z is in the intersection, that means it's in both things, which means on one hand pi of Z is Z, on the other hand pi of Z is 0. So of course Z is 0, the intersection 0. And then we notice this uber sneaky formula. That's in U again, and this short calculation shows that it's in the kernel. Consequently, everything is in U plus W, which shows that U and W form a direct sum decomposition of our FG module V. Again, supposing that you could actually find such a pi. Now, so the next step here, oops, where was I? Oh, I'm sorry, I'm too close. Oh man, what the? Okay, apparently I scanned them out of order. Great, good job. Yes? Question? Oh, okay, I thought I saw motion. Let's see here. It was nothing. Where was I? Okay, so since U is a submodule, an FG submodule, that means in particular it's a subspace of V as a vector space, right? So we certainly can find a W naught which is complementary to U in the sense of a vector space direct sum. Now the reason that this is not necessarily the kind of we want W to be an FG submodule, which means it's not only a subspace, it's also a subspace which is invariant under the action of the group, right? It has to be a G-stable subspace. And that's not given for W naught. Like this construction is just vector space theoretic. We take a basis for U, extend it to a basis for V. The things in the extension that aren't in U automatically span a subspace. That subspace we call W naught. And it's that construction necessarily gives us an independent subspace W naught. But again, this is just a vector space construction so far. So this pi naught is a projection in the sense of vector spaces defined like so. But the thing I don't know, in fact, is probably not true. It's not true that like pi naught of g dot v is equal to g dot pi of v. Like that, I don't know that that's true. So that means that if I don't, I mean, this I need for it to be a homomorphism of FG modules. Like this is one of the things that I need. And I don't know that for this pi naught. All right? In fact, I don't think it's true, generically speaking. So following Dummett and Foote, we take this pi naught and we sort of conjugate it by the group action, in a sense. Specifically in this sense, we take g pi naught g inverse of v is equal to g dot pi naught of g inverse dot v. Now, so again, U is an FG submodule V, which means U is a G stable subspace. G of U dot G dot U is in U again. This is discussed in more detail on page 483. So I found a way to make this complicated last time, but it's really not that complicated. The point is that since G inverse dot V, that pi naught of G inverse dot V is an element of U, right? By construction, we have that that's a projection onto the U subspace. So then G dot something in U is again in U. So consequently, G dot, G pi G naught inverse of U is again in U. And that means that we have satisfied criteria 1 for this conjugated, this sort of conjugation of pi naught. It's not strictly speaking a conjugation, but let me just use that as a device to not keep saying G pi naught G inverse, because that's not especially exciting. So this conjugation of pi naught is a linear transformation, which is a projection on U. Again, this thing, I also do not have that is G stable. There's no guarantee that this is G stable on W. All right. Anyway, so that's still not the thing I'm looking for, but at least it satisfies criteria. It satisfies 1 and hence 2 for all G. But oops, yeah, I got to go back to my second page because I scanned it out of order. Idiot. Me, not you. I know you know that. Let's see here. Okay, so if n is the order of the group, which is not 0, in other words, in characteristic, we're dealing with a field of characteristic not equal to n, right? Or also not equal to a multiple of n, I should say, to be more precise. The point is that 1 over n is defined in our field. If that's the case, we're going to construct pi by the sum over g in the group of the conjugation of pi naught. So this is my definition for the pi that is going to hopefully satisfy properties 1 and 2 and also be a G stable. I mean, G stable. Let's see here. So first of all, each one of these is a mapping from V to U, as we've discussed. So we're adding together maps that go from V to U. We get then yet again another linear transformation from V to U, right? If you add together things that go from here to here, you still get something that goes from here to here, right? And 1 over n doesn't change that, right? On the other hand, we've also argued that the restriction of the conjugate map on U is just the identity on U. This fed U maps back to U again. So that means that pi restricted to U is, well, the restriction of a sum is the sum of the restrictions, by the way. And so we get that. But that's just the same map added together n times, which is just n times the map. N over n cancels. And that gives us the identity on U. He's very sneaky. Yes. So there I have got, of course I mean I had that before, right? But the point is I've somehow averaged over the group and I still have the identity on U. Dividing by n was the thing I needed to think about doing in order to make that happen. If I don't have that the order of the, if I don't have that the, how does it go, the characteristic of the field, if it did divide the order of the group, then I don't know what would happen then. I don't have a counterexample or anything, but you can see that this argument breaks down anyway. In any event, this gives us that pi of u is u, hence pi squared of v is pi of v for each v and v. Of course, we had all of that for pi naught as well, so what's so special about pi? Well, it's also G stable. In other words, it's a G module homomorphism. It's an FG module homomorphism from V to U. And here's the proof of that. H dot V. H is in the group. V is in V. So by definition, that's the sum 1 over n, sum over G of pi, G pi naught, H G inverse HV, right? So then you do something a little bit sneaky. You multiply by H inverse over here, right? Which we can do. It's a group, right? That's the identity. Es bueno? Es bueno. Okay, so, and I think I'm also using the fact that this goes back to the definition of it's more than just a group. It's also a module action that's going on here because there's actually a dot missing here. This is G dot vector, so we're talking about the group action. And so depending on where you put the dot, we might be using the fact that E dot, that the identity acts as a fixed, I mean, the group identity dot x is equal to x again for everything in V. That's part of the definition of the group action. The identity has to act by just, as the identity group element has to act as the identity on the vector space as well. I mean, that's, I don't know if I actually need that for this step. Maybe not. I mean, we could just trade out the G for H inverse G. Then I guess at some point I need that like associativity thing that we can take G, GH dot V is the same as G dot H dot V. I think that's needed here. So to get, I mean, if I had the dots to explicitly work it out, you'd see that we're using some of the module, the group action definitions, like there's the sort of modified associativity we're using here. Anyway, that aside, what do you got? You got this H inverse G here, you've got G inverse H here, but you know, if we let K equal to H inverse G, this is K pi naught K inverse dot V, right? For G and G, but if you think about that, we're dealing with a finite group. What values does K attain if we let G range over all the elements in the group? All the elements in the group, right? So this is entirely the same as the sum over K and G of K pi naught K inverse V, right? 1 over n. And I just pulled the H out because H is constant over the sum, right? H is fixed but arbitrary here. So I can pull that out of the sum like that. And then I've got H pi of V, which is what we want. That shows you that pi is not just a projection in the sense of vector space. It's also got the necessary interaction with the group action to give us an FG module homomorphism. And there, from that, we get Maschke's theorem. Yeah. This argument to me is very interesting. I mean, it's a center of mass argument, right? Think about this. In physics, if you ask the question, can I invent a new part, given n particles, right? Can I invent a new particle with a different mass? So again, you've got n particles, mass 1, mass 2, mass n, right? They have position vectors r1 through rn. They have velocities v1 through vn. So here's the question. Can you create a new particle, which is a composite of these, that has some new mass, some new position, some new velocity, some new momentum, such that it obeys Newton's laws? The argument that supports the conclusion of that is essentially Maschke's theorem. What you do is you take the literally mass weighted average for the center of mass, right? What is center of mass? You guys know? You guys remember this, right? So big R, center of mass, 1 over the total mass, right? Oh, I'm sorry, 1 over the total number of particles. What is it? No, it's 1 over the total mass. Sum I equals 1 to n of mi ri, right? I mean, this idea of, you see, I mean, it's the same kind of idea, right? The center of mass construction and this construction of pi naught. There's a few places in math that involve this sort of argument. They're very sneaky arguments, but I think they're really, really powerful. and to me, unexpected. So I wanted to make sure I shared this with you because I think it's really interesting, this proof. Although I don't know if I'm actually going to do anything with it, right? Here, I'll show you. Let me show you something while I got this out. If I can find it. That's a big question. I'm sure I've showed some of you this before, but I'm not sure if I've showed all of you. Actually, I'm not sure I've shown any of you this. I may or may not have. Remember. I can't remember. If I can find it. That's the question. Ah, there it is. So this is a talk I gave in a representation of the algebras class I took in graduate school. And so what I did was I gave this little talk about representation theory and quantum mechanics. And here we're actually looking at representations of Lie algebras, right? So that's a little bit different, but much the same. I mean, they're algebra representations. And see here if I can get to the point quickly. So start this. The first chapter in this story is isospin symmetry. Isospin is based on the fact that protons and neutrons are much alike. They have very similar mass, and so you invent this thing called isospin, which says if you take isospin plus on the neutron, you get to the proton. If you take isospin minus on the proton, you get to the neutron. And so there's this isospin doublet. And turns out that this has to do with little SU2, that's the Lie algebra of special unitary matrices. This is their bracket. That's my favorite. That's the Levi-Civita symbol. That thing that builds the cross product is also in the Lie algebra for little SU2. And, yeah?
If you're interested in more about it, that's...
Oh, you have, is that Georgie's?
Yeah.
Ah, yes, I lost that book a number of years ago.
Yeah, well, the library has its own.
If you can understand that book, that's wonderful.
I don't, but...
Yeah, I like the little yellow book. Did I show you the little yellow book?
I own my own copy of that.
That one is much, I think, easier to understand. But he's very flowery and physicsy. It's not bad to look at, yeah.
I used some of his stuff to write my petition paper.
Oh, good.
It would sound impressive.
Yes, it does sound very impressive, but...
I'm pretty sure Dr. Nutter knows what physics means.
I see. Well, yes, Georgie's book sounds very impressive. I just will say from personal experience, when you try to calculate with it, well, I don't know. Okay, so anyway, so this is the neutron, this is the proton, they're eigenspace. They're eigenvectors of isospin with these quantum numbers, minus 1/2. The eigenvalues are quantum numbers, minus 1/2, 1/2. Anyway, long story short, people did a bunch of experiments in nuclear physics. They discovered these things called pions. There's a pi plus, a pi naught, a pi minus. And interactions of pions with protons and neutrons suggested that pions also had isospin of, let's see here, 1, 0, or minus 1. And so you can think about conservation of isospin in these interactions in a meaningful way. And it sort of tells you which interactions can happen and which can't through the way quantum mechanics interfaces with representation theory. Through that, people eventually came to understand something called hypercharge, which has to do with isospin and this Y, I think, is the hypercharge. So charge is related to the third component. What was it? I don't know. It's been a while since I've really gotten into this stuff here. Anyway, the neutron and proton has Y equal to 1. The pions have Y equal to what? 0. I said we find these particles are eigenstates of the charge operator Q hat with eigenvalues Q. These are literally like the charges you learn about in physics 232. I'm not talking about some kind of funny abstract charge. I mean electric charge, right? Of course, neutrons and protons don't have charge 1, do they? Like you'd think a proton maybe has charge 1 if we're using those units, whereas the neutron has charge 0, right? But they both have hypercharge 1 is the thing. Anyway, these are the Gell-Mann-Nishima relation. They reproduce the known charges as the neutron, the proton, and the pions. And as we got better and better toys, we found more and more particles. And the isospin and the hypercharge we'd learned about from the pion experiments and neutrons and protons continue to play a role in sort of organizing what we saw. But we found this sort of, it was called the particle zoo, tons and tons of particles. You've got your kaons, your pions, these eta, these are mesons, I think, the kaons, over here. Neutron, proton, these are the sigma particles. These are, I forget what that, you guys know what that is? They're baryons. Thank you. Yeah. You're right, they're baryons. That is true. But I forgot the name of this stupid symbol.
Oreo?
What's that? The Xeons. Oreo. So a way to think about all of these different things is they're essentially sort of higher energy states of the neutron or proton. Like if you sort of whack a proton really hard and excite it to a higher state, it might be one of these things. Then you had this baryon decouplet, where you've got those guys again, and those guys, they're up here, and now these guys. And the interesting thing, all of this was discovered in the mid-50s to early 60s, and then they organized the data, and it looked like when you organize it using hypercharge and this third component of isospin, they fit this nice pattern, and everything here was discovered except for this omega minus. So of course, after you see this pattern, you got to be like, we're going to find this, right? And in fact, that was one of those times where we actually predicted something in physics using abstract algebra, by the way. This is abstract algebra. Group representations, really? Well, okay, Lie algebra representations, fine. You got me. It's almost abstract algebra that you've learned, almost. And it made a real physical prediction in the mid-60s that we actually bore out with experiment, this omega minus. People got Nobel Prizes over this, I think. Not surprising. But then the main question is, okay, so there's a symmetry. These particles fit this pattern. Why? Why? And so what we figured out, the next step in the game is largely is how do you build such a representation? You build it from SU3 representations. These things you have. Let's see here. Let me get to the point. I don't need to go through all the details with you guys. Bottom line is there's these things called quarks, and these quarks, they are representations of SU3, a 3 and a 3 bar as they're called. And so this is what they look like in this graphical way of talking about the representations. And it's really pretty when you take the tensor product of these representations. It looks like this. So you take the tensor product of one quark and another. Let's see here. This is one quark and one anti-quark. Then you get different possible states from just like vector addition, basically. That's the way it ends up working. And so when you look at what those are, and you combine the hypercharge and the quantum numbers of these, you get the quantum numbers add in a precise way, and they match the quantum numbers which are known for the observed particles, which speaks to the existence of quarks. The fact that you can take tensor product of quark representations and get the same data that you've observed these composite particles having, it speaks to the underlying existence of the quarks, even though there are various physical reasons that we cannot observe quarks in isolation. They have fractional charge. They've got like a third of the charge of the electron, something like that. And we have, as far as we know, only ever observed integer multiples of charge. So they seem to be, you can't isolate a quark, and yet this speaks to their existence. And there's more. You can build the proton. So that's 2 quarks. That gets you the nonet. And then baryons are built from 3 quarks. You take what we did with 2 quarks and then add yet another layer, and then that gets you to the thing before that had the omega minus, and also this. So there's this piece with the omega minus, and then this direct sum, which also has the neutron, the proton, and these lower. Yeah, these are not the same. I'm sorry, I said these are the same earlier. They're not the same. These are excited states of those guys or something like that. I don't even know the names of them. Like I said, it's a zoo. But the point is, if you study quarks and their representations, and you learn a little bit about the representation of the algebras, you can explain the way quantum numbers are assigned to particles and the way they interact when they smash together. Like there's certain things which are conserved, which are not conserved, interactions which are forbidden or allowed. All of these things come from the representation of the algebras. So anyway, and of course this talk is naive in the sense it has completely ignored the discussion of assigning spin to quarks, and that's a whole other story. And well, anyway, I think I like this. It's one of the, I keep using this because I think it's, you can actually see it, right? Even if I don't explain you all the details, you can kind of see how we're building things from quarks, even if you don't understand all the quantum mechanics or anything. You can actually see why people believe that there is such a thing as a quark, even though we can't observe them in isolation. The fact that you can build the patterns that we need to have neutrons and protons makes us think that there is such a thing as a quark. It's kind of neat. What's that? Anything below a quark, that's the reductionist dream, right? Is that there's something else below it, right? Yeah, we don't know. I mean, string theorists want there to be strings down there, but you know, let's see here. It's how to sort of throw some cold water on that. I mean, so going from, I mean, we've had various stages of development over the past century and a half in physics, right? We started out at the beginning of the 20th century not really being sure that there was such a thing as an atom, right? I mean, when Einstein wrote a paper on Brownian motion of particles, that was a theoretical paper because we weren't entirely sure there were atoms. We thought it might be some sort of like gelatinous something that didn't have that kind of, but as experiments went on, like the concept of there being an atom or molecules became pretty well developed, right? And then we learned that inside those there was a nucleus, right? That's like really localized, and then there's this electron cloud or something. Well, the whole electron cloud idea is a little bit later. But then, going further down, we learned that the nucleus had constituents, right? Neutrons and protons, and that we could build the nucleus from smaller things. And then the quarks, right? But sort of the difference in scale each time is not too far removed. I mean, they're different scales. Usually something like 10 to the third in terms of size. God has arranged the universe so that it's decoupled. The amazing thing is that at every level we can study physics in such a way that our ignorance of everything below the scale which we can look at doesn't hurt us in our understanding. That's amazing that happens. And that's why people on the other side of the philosophical aisle are driven to believe in multiple universes and things, because otherwise it's just too fantastic to believe, in a nutshell. But below that, like strings, is not like a 10 to the third distinction between quarks. Like strings would be 10 to the 20th or something. I mean, it's way, way past quarks what strings are. So it's very, very greedy to think that we can generalize that far down, that deeply, jumping from quarks to that. Like, if history is sort of more usual, it would seem like there should be some idea below quarks, which is like a 10 to the third kind of progression, not a Planck scale progression. But on the other hand, string theory makes its own arguments in terms of how it interfaces with general relativity and mathematical necessity, and just its success in producing new mathematics. There's definitely got to be truth in string theory, some kind of truth, because we have solved topological problems that we couldn't solve before by studying string theory. There's something to string theory. What it is, whether it's physical, I think that's an open question. We've also been solving problems in nuclear physics related to what's called the non-perturbative sector. So in field theory, power series play a big role. Like in most of quantum mechanics, we can't actually solve equations like you guys do in courses. We have to use series approximations. That's all we have, the perturbative domain, right? But there are non-perturbative effects, things which you cannot describe with adding terms. And there just happen to be these mirror limits between 11, or maybe 11, or I forget if it's 11 dimensional, but some realm of supergravity happens to be dual to a non-perturbative part of QCD, which is quantum chromodynamics. So if their idea is right, they can do non-perturbative calculations in supergravity, which have meaning in, excuse me, they can do perturbative, I think, calculations in supergravity, which have non-perturbative meaning in quantum chromodynamics or something like that. This is, but that's relatively recent. Like, I have seen nuclear theorists who couldn't care a bit about hidden dimensions or anything. listening to string theorists because maybe it gives them a way to calculate things they couldn't calculate before about very physically interesting things, things that would matter to, I don't know, maybe like a star's mechanics, something like that. But these things are very much open questions. Like, it's really exciting time to be alive. String theory turns itself over, it seems like to me, every 3 years or so in terms of like its understanding of things. And there's a very similar story going on in mathematics called the Langlands program, which is also this sort of fantastic conjecture about patterns between things we don't understand. The Langlands conjecture, the Langlands program. Gluons, yes. So gluons are they are the force-carrying particles for the quantum the color force. They're what keep the quarks together. They are unlike photons in the sense that if two photons cross each other, they don't attract each other. They just kind of just go as far as, to a good approximation, I think. Gluons, on the other hand, are not like that. You can have these things called glue balls, where you have a bunch of gluons together in this glue ball. And then there's this thing called the quark gluon plasma, which people at Stony Brook studied when I was there. They all get very excited about, have they observed the quark gluon plasma? It's like, when you go to a talk in nuclear physics, you'll find out that there aren't 4 states of matter. There are something like 17 or 18 states of matter. Because you can talk, every state of matter is defined by a phase change. It's when something becomes free that wasn't free before. So like, you guys are familiar with gas, solid, liquid, right? Plasma, what's the difference between plasma and ordinary matter? What is that? You probably know, Lorenzo. Yes, the electrons are free. That's what's free. So you can start, you can keep going up this, heating things up and freeing various aspects of the matter. And every time you do that, you get to some new state of matter. And somehow they're 17 or 18. I can't enumerate them for you, but nuclear physicists, you ask them, they'll show you. All right. So yeah, go find the nuclear physicist on campus here. And you can ask, well, actually, you could ask her. We have one. Ms. Stromby actually has a master's in nuclear physics working on such an experiment. I'm actually not joking. She might actually be able to tell you a few more states of matter. You should go ask Ms. Stromby. Name me a few more states of matter I want to know. She might know. Extra credit. You'll bring me. I think my health would be in jeopardy if you brought me some of these states of matter in any quantity. Like, here, have some fire. That's what plasma is, right? It's the 4th state of matter is fire, give or take. All right, now we come to Wedderburn's theorem. What is Wedderburn's theorem? You thought there were 50 states. Make matter great again. Let's see here. So this is Wedderburn's theorem. I became I became aware of this theorem as I was working with some students on the associative calculus research stuff I've been doing the last couple of years. Became aware of this early on, actually. Here it is. Let R be a non-zero ring, unital ring, not necessarily commutative, then the following are equivalent. I will skip 1, 2, 4, 5. Fine, I'll give you 4. The ring considered as left R module is a direct sum. The direct sum are L1, L2, Ln, where each L sub I is simple module. It's a simple left ideal with L equal to R EI for some EI in R with, so I don't really care about all these details, EI, EJ. This is really not the one I want. He must have a corollary, which is what I think of as being the theorem. I'll find it in a second, guys. I mean, this is lovely, but this isn't really, I mean, he has really nice other descriptions, but we haven't really gotten into those other things. Like, 1, he says every R module is projective. 2, every R module is injective. 3, every R module is completely reducible. This is 4. 5, oh, 5 is what I want. I'm an idiot. As rings, R is isomorphic to the direct product of matrix rings over division rings. R is equal to R1 cross R2 cross R, R, where R is a two-sided ideal, R sub j. Of R. And R and R sub j is isomorphic good grief, isomorphic to n sub j, why didn't I write this out? Poor planning on my part. N sub j by n sub j matrices with entries in a division ring, delta j. He says the integer r and the integers n sub j and the division rings delta j up to isomorphism are uniquely determined by r. Boy. So I think, I'm trying to think here. I think sometimes 4 is, Daniel, what would you say 4 is, if you wanted to give a name for that? When something can be written, when something is not simple, all right, but it can be written as a direct sum of simple things. I think I usually call such a thing semi-simple. So I think this is semi-simple. Now, this is not saying that every ring looks like this, right? It's saying that the following are equivalent. So this is basically telling you what semi-simple rings look like, right? Now, what's a division ring? So let's suppose that the ring is R for a second here. What would a division ring look like? How is this delta J related to? I mean, let me just get to it. Well, I don't want R to be R. I'm sorry. No, that's not what I want at all. Oh, man. Curses. How to say this? So here's the main application I'm interested in. All right. If A is a semi-simple associative algebra over R, then what does Wedderburn's theorem tell us about A? Right, it says that A is something like R, let's see here. Oh, goodness gracious. Yowzers. Stink. Well, I guess A1 AR, right? What do these look like, though? These A sub R's, these things? They're isomorphic to Nj by Nj matrices with entries in a division ring. So, for example, it could be something like R cross what I would call R sub 2. You know, or it could be C sub 3. R sub 2, what is that? That is A, B, C, D, such that, you know, the set of 2 by 2 matrices under matrix multiplication, right? Those are entries in a field, I mean, a division ring. So here, what are the, I mean, the thing is, for a semi-simple associative algebra, the things that you're breaking in the direct sum of, they still have to be, they have to respect the reals here. So basically you have choices. What are the division rings which contain the real numbers is really the question I'm trying to get you to see here. There's only 3. So I'm sorry, Lorenzo, I started late today. You're fine, go on.
Is it just an example of a decomposition? Or what is, can you explain that again?
This is an example, yeah. That is an example.
What do you mean by R sub 2?
Well, it's the matrix. It's fine, but this division ring, for this example, it means that you've either got n by n real matrices, or you've got n by n complex matrices, or you've got n by n quaternionic matrices. If your algebra is commutative, it means it's the direct product of just copies of R and C. Because you can't have an H, it's non-commutative. The regular representation of this is really fun to look at. We'll do that and then we'll stop. So if I have, what happens when you multiply 2 matrices? You get a new matrix, yeah, thanks. That's very helpful. Let's see here, so AX plus BZ, we get CX plus DZ, we get AY plus BW, we get CY plus DW, right? So if I want to look at, so I can look at A, B, C, D times X, Y, ZW equals to AX plus BZ dot, you know, CY plus DW. So basically R4 paired with this weird multiplication is a representation of R2. That is a faithful representation of the 2 by 2 matrix algebra. The regular representation then, like what is the matrix of A, B, C, D? It'll be helpful for me to write these out. Actually, let me write this out in a little bit more suggestive way. AX plus BZ, AY plus BW, CX plus DZ, CY plus DW. So we get A 0, B 0. Oh, I'm sorry. I'm an idiot. That's the first row. That's from this one. And then this matrix times XYZW should give us this. Is what we were doing last time. Well, not last. I don't know when we did it, but we did it. And then 0. There's a mystery here I'd like to ask you guys. I'm trying to get something here. And then I'll stop. I really will. C, 0, D, 0, 0, C, 0, D, right? What is that? Right. Which one tensor? Which one is it? Yeah. So the left regular representations of the matrix algebras are all like this. They're just tensor products of the identity, like that. Well, something like that. So they're kind of interesting. Well, I think they're very interesting. But the most beautiful part of the calculus that we've worked out is for the semi-simple commutative case. If you drop semi-simple commutative, still it gets uglier because you have nilpotent pieces. If you drop commutativity, then you get the matrix algebras to deal with in the semi-simple case. And if you drop semi-simple and just say associative algebra, then that's the wild unknown for me. There's nasty stuff out there. I mean, there's a lot of stuff to study. But anyway, that's just a slice of life here in terms of associative algebras. I hope you enjoyed this semester. I will try to help you out in terms of understanding test 2 next time. Hopefully I'll have an understanding of it. I'll just call you guys up to the board and let you explain the problem you understand. How about that?
So I went first.
What's that?
I went first.
As long as you're first. Ah! Very good. Thanks, Daniel.